Good afternoon. We are in the VLab seminars, and today we have Robert Cardona, who is postdoc at UBC, and who will talk about dynamics and transversality via symplectic flexibility. Welcome, Robert, and start when you want. You can start.
Okay. So, well, first, thanks for inviting me to speak here. So today I will be speaking about some. So this is a joint work with Francisco Presas. Well, it's in progress. I mean, the statements are not in the last form, and so it will be very introductory. So I wanted this to be useful also for Alberto and Pablo. So I will try to. I mean, at the very end, I will give one proof, maybe sketchy. But mainly I will try to motivate the question and the statements. So, well, a symplectic manifold will always, in general, be closed, but we will also consider open ones for some statements. And, well, just recall that a symplectic manifold is a manifold endowed with a two-form that is non-degenerate. So here the manifold is of dimension 2n. And closed. It's a closed two-form. So if you choose one hypersurface which is co-oriented, you can restrict. So if I is the inclusion of omega into M, you can restrict your two-form, and then you will have a two-form that is of rank 2n minus 2 in a manifold of dimension 2n minus 1. So in particular, it spans a kernel, which is a line field. So this is what I will call a Hamiltonian structure. So if you pick an odd dimensional manifold and a two-form which is maximally non-degenerate, so in this case it means that it has rank 2n minus 2 and is closed, then it's called a Hamiltonian structure. So this is also called in some other places of the literature an odd symplectic structure. But I prefer this one because it has to do with Hamiltonian dynamics, let's say. If anybody has a question at some point, just ask, because this is like, it's going to be very important. So as I was saying, when you restrict to an hypersurface in a symplectic manifold, you get a line bundle which is defined along omega. And so why is this related to dynamics? Well, because so as you might already know, if you have any function h in a symplectic manifold, it defines a Hamiltonian vector field by this equation. So it follows from this equation that h is what's called a first integral, no? If I contract again with x, I get this equation, which means that x is tangent to the level set of h. So if h there's a regular level set, then you get an hypersurface, and the vector field is tangent to the hypersurface. So what happens is that when you fix an hypersurface and you look at this kernel, which is a line field, what happens is that for any Hamiltonian for which this hypersurface is a regular level set, the Hamiltonian vector field will be tangent to this kernel. So it doesn't depend on the Hamiltonian function. It will always be tangent to this kernel. It only depends on the hypersurface, or if you want, in the embedding, no? So for example, if you are looking at the unit circle embedded in R2 with the standard symplectic form, so of course, if you restrict your two form into a one-dimensional manifold, you get just the zero form, and the kernel is the tangent space to the unit sphere. So this is a line bundle, no? Which is here drawn in red. Then what will happen, for instance, if you take as Hamiltonian function the radial function, the Hamiltonian flow along this level set will be exactly partial theta. So a more complicated example is in R4, again with the standard symplectic form. And then you pick the unit 3 sphere in R4. And when you restrict omega standard it's omega standard, the kernel is tangent to the Hopf fibers. So the vector field will have all the orbits closed, for example. This is a dynamical property of this kernel. And again, this Hamiltonian flow is given by, for example, the Hamiltonian flow of the radial function, which contains the unit sphere as a level set. So, well, in general, when one wants to study the dynamics of Hamiltonian vector fields, since you already know that it's tangent to the regular level sets or the level sets in general, it's easier to just study the restriction because you get one less dimension. So this is one way to do this. Well, one way that this has been done, rather, is to ask whether the hypersurface has some other properties which will tell you something about the dynamics. So, for example, if omega, so omega is the hypersurface in M, admits what it's called a transverse Liouville vector field. So this means that there is some vector field that it's transverse to the hypersurface and satisfies this equation rather. So that it sends omega to omega by the flow. Then what happens is that if you restrict this one from here, which is the contraction of omega by the Liouville vector field, this is what it's called a contact structure. And the Hamiltonian structure that it's associated to it is just the differential of this one form. So this is the Hamiltonian structure. So when this only happens when you have this Liouville vector field transverse to it, and then we say that omega is a contact hypersurface. And well, this defines contact structures. No, in general, a contact form, if you fix a form, is given by a one form which satisfies this equation here. So this is exactly what it's satisfied by this alpha restricted to omega, to W. So this from a geometric point of view, this alpha defines an hyperplane distribution given by the kernel, and it's maximal in all integrable. So for what it means is that it's at the very opposite side of the spectrum of Frobenius theorem. So Frobenius theorem will be this one. This means that the kernel of alpha defines a foliation, and the contact condition is the opposite. It's like up to the maximal degree, it's non-vanishing. And this means, that you can see in this picture, that you cannot find tangent submanifolds of, let's say, dimension 2 here. And this is the...
Well, sorry, maybe it's a silly question.
No.
This is omega to the 2n plus 1, maybe, or it's...
No, because, well, so if you have... Wait. Yes, so either this is plus 1, or
okay.
minus 1. Yes, sorry.
But, okay, thank you.
It's n minus 1.
Okay.
Exactly. Okay. So in R3, for example, this is the example that is pictured here, and actually every contact structure is locally of this form, because contact structures also admit a Darboux theorem, like symplectic manifolds. So for a contact form, if I fix a contact form, there is let's say a privileged section of the kernel of the alpha, no? So the kernel of the alpha, as this is the kernel of a Hamiltonian structure, so it's well defined, it's just a line field. And if you normalize it by this condition, so this only means that R is in the kernel of the alpha. If you normalize it, you get what it's called a red field. the rep field defined by this contact form. So this rep field is exactly the line field in the kernel of the Hamiltonian structure. So if you have a contact hypersurface, any Hamiltonian function which has this contact hypersurface as a regular level set will have a vector field which is tangent to the rep field. So the Hamiltonian vector field will be tangent to this rep field. So as I was saying, the conclusion about this discussion is that in general, you wanted to know or to study the dynamics of a Hamiltonian vector field by just looking at this kernel, no? At the Hamiltonian dynamics induced on an hypersurface. For example, an example of this approach is the Weinstein conjecture, which says that any rep field admits a closed periodic orbit if the contact hypersurface is closed. So of course this is interesting because this tells you that if you give me any Hamiltonian vector field, for instance, the three-body problem and so on, if you find an hypersurface which is of contact type, then you can already say that there's a periodic orbit, etc. So this is known in dimension 3, for example. This is proved in dimension 3, and not in general. Another thing is that you may ask is, well, okay, if your Hamiltonian structure is of contact type, let's say, you know that there's a periodic orbit, but does this hold for any Hamiltonian structure? So in general, a Hamiltonian structure will be this omega which is closed and satisfies this condition in a manifold of dimension 2n-1. So the kernel, perhaps it doesn't have a periodic orbit always. So only when omega comes from a contact structure. And so this was proved by Ginzburg. I don't remember the year. So he proved that there is a sphere, a 5-dimensional sphere embedded in the standard 6-dimensional symplectic space, such that the kernel has no periodic orbits along this sphere. So in particular, well, okay, the Weinstein conjecture is not proved in dimension 5, but it's not disproved neither. So this is not of contact type. In dimension 5, this Hamiltonian structure is not of contact type. But this means that, well, there's a difference. Like being contact imposes some conditions. So the question that I will be addressing.
Well, maybe you can say also how how this is called, like if in the last slide, like this example there of this 5 sphere, because I think he calls this as like the counterexample to the
yes.
To the Hamilton-Seifert conjecture, right?
Yeah. Yes. So the Seifert conjecture, this is good. So there is another conjecture which is related to Weinstein conjecture, which is Seifert conjecture. So this conjecture says the first statement, let's say, says that a non-vanishing vector field in the 3 sphere always has a closed periodic orbit. Okay, so every x admits a periodic orbit. So it was proved that this is not true. Well, there are several. So first it was proved in the C, I think it's C1 for a vector field which is C1, and then in the smooth category and analytic category, this was proved by Kuperberg. That there's a non-vanishing vector field which does not admit a periodic orbit. So this conjecture is false, like this. But you can ask the same thing, changing, let's say, the hypothesis. You can say, okay, is there a volume-preserving vector field that has no periodic orbits? And this is not known in the 3 sphere. But you can ask also this in higher dimensions. Like in S5, for example, there are volume-preserving vector fields which do not have periodic orbits. So what Ginzburg proved is that not only it's a volume-preserving vector field, but you can also ask that it's a Hamiltonian, well, it lies in the kernel of a Hamiltonian structure. Or if you want, that it's induced by a Hamiltonian vector field. So this is why he calls it a smooth counterexample to the Hamiltonian. This is the name of the paper, I think. A smooth counterexample to the Hamiltonian Seyfert conjecture. Counterexample to the Hamiltonian Seyfert conjecture. Okay. All these counterexamples are constructed using what's called plugs. But what you do is you construct a vector field which has only a finite number of periodic orbits, and then using a flow box along this orbit, you kill it by introducing a plug. So this was done by Kuperberg, and Ginzburg did a Hamiltonian version of a plug. Okay. So the question that I will be discussing in the first part of this talk is, so this is more or less the hand-wavy question, which is, can the rep dynamics, so this is in the contact setting, or Hamiltonian flows in general, in the sense of the kernel of a Hamiltonian structure, contain arbitrary dynamics? So let me put a question which is more precise, because this is not precise. So let's say I start with a compact manifold N and some vector field which has no zeros. So there's two questions. So you can ask it either for contact geometry or Hamiltonian structure. So is there a contact form or a Hamiltonian structure omega in some sphere of high enough dimension and some embedding of N into this sphere, so that the kernel is tangent to N and becomes the vector field X? So let me picture it because it's easier. So you have N and some vector field tangent to X. You embed it into some sphere where you have some Hamiltonian structure or some contact form which defines a rep field. And the question is whether you can find one. So you can find one Hamiltonian structure such that it coincides with X along this embedding. So in some sense, the dynamics of this vector field here are embedded into the dynamics of the rep or the Hamiltonian vector field. Everybody understood this question? Okay. But
Sorry.
So what we proved back in 2019 with Eva, Miranda, Daniel Peralta Salas, and Francisco Presas, in what we solved somehow is this question in the case of a contact structure. So a necessary and sufficient condition to embed a vector field into the rep vector field of some contact structure is that X has to be geodesible. So it's not true in general. There are vector fields which cannot be embedded into the rep field of a contact structure. But a necessary condition is that it's geodesible and it's also sufficient. And what we did is, well, we proved a more general statement, but we proved that the embedding exists, and we computed one possible, let's say, one dimension, which was the smallest that we can prove, which is this dimension here. So what this part here is saying is exactly what I'm saying, that there is a contact form so that the rep vector field, which is tangent to the kernel of the alpha, coincides with the push forward of X. So what now? This I started looking at it a few months ago, and then I started working with Fran in a very related problem. So this is what this became a joint work with Fran. But we are going to do a more general statement. So let me just give you a few, let's say, I don't know. This is just some statements, but we will do some more general statements. So in the Hamiltonian case, so let's say now I'm fixing an odd dimensional sphere, so it has to be odd dimension. And the statement is that given any vector field, now I don't need it to be geodesible. There is an embedding of the manifold N and the vector field X into the sphere of dimension 2m-1. With 2m-1 has to satisfy this bound. then, sorry, not even, this is odd. Such that the kernel of the Hamiltonian structure becomes tangent to n and coincides with the vector field, which was arbitrary. So again, the picture is like the one I draw here, no? Here. So if the dimension of the sphere is at least 3 times, more or less, the dimension of n, you can find a Hamiltonian structure that becomes, well, whose kernel becomes tangent to the embedding of n and coincides with x. Well, and as I was saying, this is just one statement, but you can prove more things. Like you can prove that any Hamiltonian structure in the sphere is homotopic to one which satisfies this condition, and what else? And you can also, so in this statement, you can also fix the homology class of omega. So omega is arbitrary. So this is a class in H2 of M. So this is arbitrary. And if you ask that this class is 0, so that your 2 form is exact, then you can say more things, like any embedding, like you can fix your embedding first. So you pick any embedding of n into the sphere, and you pick an exact Hamiltonian structure, and then you can deform it through Hamiltonian structures to one which is tangent to n and so on, and coincides with x. So here I'm just...
Robert?
Yes.
I don't understand your observation here. In fact, any Hamiltonian structure is homotopy to an omega tilde above.
Yeah.
What do you mean by
so
this?
in the statement of the theorem, I just said that there exists one, no? So there exists some Hamiltonian omega tilde such that the kernel coincides with x along the embedding. So what I claim here, so this is not precise, but in fact what you can say is, so start with any embedding E of n into Sm. So a smooth embedding with M satisfying this. And omega, some exact Hamiltonian structure. So you fix an ambient Hamiltonian structure. Then there is an homotopy of Hamiltonian structures. So there is some omega t such that omega 1 contains these arbitrary dynamics in n. But you need it to be exact for this to be true. This is because of a cohomological condition and so on. Okay. So here, what I was saying is that in this theorem, I'm just speaking about a Hamiltonian structure on an odd-dimensional manifold. Now I want to say something about the ambient symplectic manifold. And the message is that up to adding a few more dimensions, you can fix the ambient symplectic manifold. So this is another statement. So what this statement is saying is that, in fact, did I draw this? So you can pick the R2M with the standard symplectic structure. Here you have the standard unit sphere. And recall that the Hamiltonian structure induced in this unit sphere is just the Hopf fibers. Well, the kernel of the Hamiltonian structure is the Hopf fiberation. So this generalizes in any dimension. So what you can prove is that there is a C0 small perturbation of the sphere such that, you pick some embedding of n into this sphere. Any smooth embedding. It exists because of Whitney's theorem. And you pick any vector field in n. So this is a vector field. Your vector field X is defined on n. So there is a perturbation, C0 small perturbation of the embedded unit sphere into some sphere S2m minus 1, but with a tilde because I perturbed it, such that the Hamiltonian flow of the radial, let's say, any Hamiltonian function which contains this sphere as a regular level set will induce a Hamiltonian flow which is tangent to n and tangent to x. So it induces this arbitrary dynamics. So this is what is written here. I was trying to explain without reading the statement. So I pick any vector field x on a closed manifold n, and there is an embedded sphere H, an embedding from S to M minus 1 into R to M, which is C0 close to the unit sphere, such that this happens. So the kernel of the symplectic form pulled back to this sphere is tangent to X along N. So to say, instead of saying I'm not saying now that there is some Hamiltonian structure which is tangent to this n and so on, but I'm saying that this Hamiltonian structure is induced by restriction of the standard symplectic structure. Is there any question about this statement? Okay. So you might notice, but I think this can be improved. But as it is proved right now, I had to add 2 dimensions here. So now it's 3 times plus 3 instead of 3 times plus 1 as before. So the proofs use the so-called homotopy principle or H principle. And now I will give a very short introduction to what, well, very hand-wavy of what's the way of thinking about this. So if you take any partial differential relation, so this is more general than a PD. It's like, let's say, yeah, I don't know, like an ODE will be a partial differential relation, but you can also ask, like, I don't know, if you have a function h, you can ask h prime greater than 0. This is not an equation. This is an inequality on the derivative of h. So this will be also a partial differential relation and so on. So what you want to look at, instead of solutions to a partial differential relation, you want to look at formal solutions. So formal solutions means that you decouple, in some sense, the derivative and so the map and its derivative. So now I will show a very easy example. So for example, let's say I'm looking at embedded path in the plane, no? So gamma is a path from the interval 0, 1 to the plane. And my differential relation, this is what I denoted by, I don't know, calligraphic or, is so there's a path to be transverse to partial y. So to be transverse to the foliation by these leaves. So this example here, I gave you a path which is transverse to this foliation. This is clear, no? So at any point, this is transverse to the foliation by y-axis. And what I draw here in red is the derivative at each point of the path. So what I have is a pair, gamma, comma, gamma prime, which satisfies my relation. So this is what I call here a genuine solution. So it's a solution for real, it's not formal. So this here is what I will call a formal solution. So this is not a solution for sure, because if you look at this point, this is tangent to partial y. So this pair is not in this space. It's not a solution. So this path, sorry. But instead, what I'm saying is that instead of looking only at gamma, comma, gamma prime, I look at pairs which are decoupled. So I look at a path gamma and an injection which sends at each point on my interval a tangent vector in the plane. This is what I draw here in red. So what I did here is, instead of taking the derivative of my path, I take one element of the tangent space at each point. So this is different from gamma prime. This is the difference. This is why I call it a formal solution, because this pair satisfies the relation because these tangent vectors that I draw are transverse to partial y. So if you look at this is transverse to partial y. But it's not a genuine solution because H does not coincide with gamma prime. So this is what's called a formal solution, because it's a solution if you forget that it's a differential of a map. Is there any question about this?
Yes. Sorry, maybe it's the next point, but my question now would be, and why do you choose and how do you choose this H? I mean, is there any constriction or I mean, you can choose infinity and infinity for each point. You have you said one direction, you can choose any other for each point. No?
Yeah. This will depend on this will depend on your problem. But yes, so in principle it could be, well, in general you want, let me think about it. Yeah, so you want it to be, well, it depends on your problem. So for instance, in this question, the natural space to look for formal solutions are, let's say, so you need to ask before if you are speaking about immersions or embeddings, for instance. So once you fix one, let's say I'm looking at embeddings, but for immersions it will be the same. Of course, this map H has to be an injection, because I mean you want it to be at the end you want it to be an immersion, so it has to immerse the tangent space of E into the tangent space of R2.
And you want it to be smooth, the change in the
yes
in the vector field at this point. Okay.
So this map here is smooth.
Okay.
Exactly. Okay. So you can so you cannot go from here to here without smoothly deforming.
Okay. So it's like a generalization of a curve at its tangent space, so you can have. Okay.
Yes.
Okay. Thank you.
So the H principle is what you want. Well, what the philosophy, let's say, behind it is say, okay, I would like to. So let's say finding a formal solution is much more easy. This should be clear because you have much more. So genuine solutions in particular are formal solutions. So the space of formal solutions is much bigger. So what you would like to say is, okay, let's say I want to solve a partial differential relation. I don't know how to find a solution, but I know how to find a formal solution. So what you would like to know is if the existence of a formal solution implies the existence of a genuine one. And in general, because of how it's proved, what you prove is that the formal solution is homotopic to one which is genuine. So for instance, in this example, you can find a deformation, let's say, which moves your path, and the derivatives, you put them like this. And you end up with a genuine solution, for example. So if you look at this, you started with a pair. Let's call this, I don't know, H0 equals gamma 0, comma H0, which is a formal solution, and you end up with a gamma 1, comma H1, which is equal to gamma 1 prime. So here, look that you may notice that here the derivative is correct. It corresponds to the derivative of the map. So you find a family, an homotopy of path, such that for every time it's a formal solution, because you might see that I draw this in a way that it's always transverse to this, the red lines. But at the end, it's a genuine solution. So you deformed a formal solution through formal solutions to a genuine one. So when this is true, so you pick a partial how do I call it? Differential relation. So if this is always true, then you say that it satisfies the H principle. So if a formal solution is always homotopic to a genuine one. And there are several, let's say, versions of the H principle. You can ask for parametric families of solutions and more things. So the main point is that H-principles have proved to be a very nice tool for symplectic and contact geometry. And if you look at the field of symplectic topology, you always looked at, well, there's a very nice dichotomy between rigidity results and flexibility results. And flexibility is often comes in the form of H-principles. So now I will give examples of things which satisfy and don't satisfy the H-principle in geometry, in symplectic geometry. I mean, this kind of H-principles, let's say for ODEs, for example, it's trivial. It usually doesn't say anything. So either an ODE, either it satisfies or it doesn't satisfy the H-principle for trivial reasons, usually. But in geometry, it happens that it's very useful. So it has applications besides symplectic and contact geometry, like Nash, Kuiper embedding. It's Kuiper, or well, the isometric embeddings, the Nash embedding theorem. This follows from H-principles also, and for example, the how do you call this? Smale eversion theorem, which is also very famous. So Smale eversion. This also can be proved by H-principle. This and Nash isometric embeddings. Okay. So in symplectic geometry, Gromov in '86, Gromov was the one who put, let's say, took these theorems by Smale and Nash and put the framework, which was, well, all of them lie in the framework of H-principles. So he proved that contact and symplectic structures satisfy an H-principle on open manifolds. This is not true in closed in general for symplectic. So this means that if you start with a formal, which I haven't defined, formal symplectic structure in an open manifold, you can deform it to a symplectic one. So in this case, a formal symplectic structure is going to be just a two-form, which is non-degenerate. And when I say it's formal, it's because the existence of such a form is topological, is a topological question. It's not geometrical. So the tangent space of an open manifold either admits Schutz-2 form or it doesn't. And this is topological. It depends on the vector bundle structure of the tangent bundle. But having a symplectic form is geometric because you need to ask for the closeness. So what this is telling you is that the topological if the topological obstruction vanishes, then you have a geometric symplectic structure. So this is true for symplectic and for contact in open manifolds. Then in Eliasberg in '89 and in higher dimensions in 2015 by Borman, Eliasberg, and Murphy, they proved that the contact structures also satisfy this H-principle on closed manifolds, but the argument is much more, well, it's much more geometric actually. Here it's the H-principle follows from general analytic methods, let's say. But in this case, you need to restrict. So if you start with a formal contact structure and you deform it to a contact one using this H-principle, you will end up always with what's called an over-twisted contact structure, which is a very special kind. So this is what when this happens, you say that there is a class of solutions which is flexible. So if you look at solutions to the partial differential relation, let's say R contact, so this will be the partial differential relation of being contact. There are two types of solutions. There are let's say this contains solutions to R cont can be divided into over-twisted contact structures, tight contact structures. So there is two classes of contact structures. So in this case, you say that these ones are flexible. Why? Because they satisfy an H-principle. And they satisfy a much more strong H-principle, in fact, because of what I was saying. You can also ask for parametric deformations. Like you start with a parametric family of formal contact structures, you can deform it into a parametric family of contact structures. And this is meaningful because of gray stability and things like this. which I'm not going to explain. So what is interesting for us, well, besides all this, is that Hamiltonian structures also satisfy an H principle. And this was proved by McDuff in 87. But well, I mean, it also follows from Gromov as a lot of things in symplectic geometry. Well, 86 or 79, I don't know. So, well, here I also put even contact. I don't want to introduce this, but it's just to give you other examples of structures which are related to symplectic geometry and also satisfy an H principle. And another, let's say, more recent example will be folded symplectic structures, which perhaps you have heard me speaking about them. So this is not a symplectic structure. It's what's called folded. It has a singularity of very controlled. And this satisfies an existence H principle. By the way, I forgot to say that. So for closed manifolds, contact structures satisfy an existence H principle, but this is not the case in symplectic manifolds. So for symplectic manifolds in open manifolds, this is true, but symplectic structures on closed manifolds, it was proved that in dimension 4, they do not satisfy an H principle. I think in higher dimensions, this is open, but in dimension 4, McDuff and somebody else proved that there is a manifold which admits a formal symplectic structure, but that meets no symplectic structure. Another example, which is also recent, this is by Casals, Perez, Del Pino, and Presas. They proved that Engel structures also satisfy an existence H principle. I didn't introduce this, but well, it's just to tell you that, well, when you study geometric structures in geometry, it is very natural to ask whether there is this existence H principle because you reduce a problem in geometry to a problem in algebraic topology. So other objects that have been studied in symplectic topology and for which you have some H principles are immersions and embeddings. So, and in this case, it depends on the codimension. So if you look at a symplectic embedding, so you start with a symplectic manifold, and you want to know if it can be embedded into a bigger symplectic manifold, so that when you restrict the big symplectic form to your submanifold, it induces the one that you had at the beginning. So this is also usually called isocontact and isosymplectic embeddings. But you can also speak about embeddings which induce a symplectic form when you restrict, and this is contact and symplectic embeddings. So they satisfy an H principle with these conditions. So contact, well, this was proved by Gromov. Then there are better results now. So in codimension 2 for an open source manifold and codimension 4 for a closed source manifold. As I was saying, this has been improved. Well, it's okay. So in codimension 2 closed contact, this was recently proved by Casals, Pancholi, Presas. They proved an existence H principle. But it satisfies only the existence H principle. The parametric one, it was proved also that it's not satisfied. And all this is very recent. Another thing that you can ask is whether immersions transverse to a contact structure satisfy H principle. So for example, you start with, so this is an example of, well, this is the plane field that I draw here is an example of a contact structure. And what I draw in red is a knot. So it's gamma from S1 into R3, which is transverse to this contact structure. As you might notice, the plane is always transverse to your knot. So a question that you can ask is whether if you give me a formal transverse immersion, can I make it transverse? So the answer is yes. This was proved, I guess, by who? So what you can ask instead, and this is open, is whether transverse embeddings satisfy an H principle. So here you really need to restrict to immersions. So if you start with an embedding, which is formally transverse, you will end up with an immersion that might have self-intersections. So what you want to, well, what you would like is that you end up with an embedding, not only an immersion. So this is the open question here. And so what we proved with Fran is, let's say that in some cases there is an H principle. So let's say that your manifold is over-twisted. As I was saying, it's one of those two big classes of contact manifolds. Well, this is the flexible class, so it's not surprising that in this case you can say something more. And then you need to ask for a formal condition, which is this one. So if you give me an embedding which is formally transverse and admits a trivial section on the normal bundle, then you can deform it into, this is the corollary actually. You can maybe look at this corollary because it's more clear. So if you start with a formal transverse embedding with a trivial section in the normal bundle, it can be deformed through an isotopy to a transverse embedding. So okay, this is true for for so-called over-twisted contact manifolds. And in general, so if the contact manifold is not over-twisted, you can also find a flexible class, but it's much more restrictive. This let's say formal condition is quite restrictive. However, this question of having a trivial section is not so restrictive. Like for instance, in codimension 1, it means being co-oriented, which is natural. Okay, so when did we start it?
More or less 40 minutes ago.
Okay, so do you want me to give a sketch of one proof, or shall I stop here? Okay.
For me, you can go ahead. What do you think, Pau?
Yes, I think you can go ahead.
Well, okay. Then I will sketch the proof of the first theorem that I said, because it's the easiest to sketch. So the first theorem, recall that it said that if you start with so you pick a sphere and some manifold, closed manifold, and some vector field without zeros. So under the assumption that 2n minus 1 is in 3 dimension of n, plus 1, 3 dimension of n plus 2, there exists an omega tilde such that the kernel of omega tilde along some embedding of n coincides with x. Oh, sorry, this is a push forward. Okay. So this is the statement. Okay. Well, here it's okay. I will say it like this. So start with the sphere. Well, here I wrote M. So M is odd. And it's three dimension of n, yeah. So we have this condition, and I fix any Hamiltonian structure, okay? That there exists one at least, because you can, for example, look at the standard contact structure in the sphere. This is one example of a Hamiltonian structure. So by Whitney's embedding theorem, because we are in 3 times the dimension of n, there exists at least one smooth embedding of n into Sm. So this is the lemma where I'm hiding, let's say, one of the most important steps. And this is algebraic topology. And this, in fact, so the computations of this lemma, we did it already with Eva. And so this is now in our paper in 2019. Peralta Salas. You just need to restate it in a different way, but it's the same. So what this is saying is that, so I fixed a Hamiltonian structure, let me call it omega 0. And this lemma, which is, as I was saying, it's algebraic topology, it tells you that there is a deformation of this omega 0 into some omega 1, which satisfies these two conditions. So first, the deformation is along two forms of maximal rank, but what we don't know if they are closed. So omega 0 is a Hamiltonian structure, it's non-degenerate and closed, but the path is not a priori. But omega 1, so omega 1 again is non-degenerate, but it's not closed necessarily, but satisfies two conditions, two extra conditions. The first one is that the kernel of omega 1 along n coincides with x. So here I'm abusing notation, so it's along the embedding of n. And the second condition is that it's an isotropic submanifold. So when you restrict this two form into n, it goes to 0. So now what you do, and this is also a very nice trick, which we took from Eliasberg and Mishashe. So now you have n, which is an embedded manifold, in n lies in, how do I call this? M. No, sorry, into the sphere. So if you look at the normal bundle of n, it's just a bundle whose fibers are m minus n. So this U is just the normal bundle of n. And I can take, let's say, up to picking some trivializing charts, I can pick some coordinates in the fibers. So if I take a trivializing chart, I can think of n times r n minus n. So this is, you need to take an open set, let's say V. This is clear, no? I'm just picking a neighborhood of n, and then the normal bundle of V is given by R, the codimension of the embedding. So because this is omega 1. So because omega 1, this two form, which is not closed but is non-degenerate, is isotropic, this means that I can write it in this form, where T sub I are the coordinates in the fibers. So as you might, as I was saying, this omega 1, you don't know if it's closed. But the good thing is that because of this very particular form, you can take an omega 2, which is closed by construction because I'm taking it as an exact form, it's a differential of something. But for T sub I equals 0, it coincides with omega 1. Because then you're putting this equal to 0. So this is the 0 section, this is n. And this two form coincides exactly with omega 1 along n. So because omega 1 is symplectic, omega 2 is also symplectic. Symplectic, I mean non-degenerate. So because omega 1 is non-degenerate, omega 2 is also non-degenerate along n. And because this is an open condition, this holds in a neighborhood of n. So what this means is that this omega 2 is closed and non-degenerate near n. So for T sub I small. And this is satisfied by construction because omega 1 and omega 2 coincide along n. So the kernel condition is also satisfied. So here I'm skipping another step. So what you can prove is that in fact, this omega 2 can be extended because it's homotopic to omega 1, this omega 2. This omega 2 can be extended to a globally defined two form, which satisfies two conditions. The first one is that it's of maximal rank everywhere. And the first one is that it's closed near n, not globally, only near n. And satisfies the dynamical condition, let's say, that we want. So here's where you apply an H principle that it's called relative to domain. This means that, so I think of this, of a two form being non-degenerate as a formal solution. But in this case, I have a two form, which is non-degenerate everywhere, but it's closed in a neighborhood of n. So there's a part of my manifold where my solution is already a genuine solution. So this is what I draw here. So in near n, all this zone is okay. This is okay. Because by construction, omega-2 is already closed near n. But outside of n, it's not closed. It's only non-degenerate. So what you can apply is what's called the relative age principle, which means that I can deform my two-form, which is non-degenerate, into a closed one without changing what already was a Hamiltonian structure near n. So I deform this here into one which is closed. But in near the embedding of n, I didn't change it. So I end up with what I called omega-3, which is now a closed and non-degenerate two-form that satisfies the condition that I wanted. Because near n, it's omega-2, which already satisfied it. Was this clear? More or less the idea. Okay. So that's it.
I love this picture.
So thank you, Robert, for this nice talk and conference. Now it's the time for questions. Does anyone have a question for Robert? In fact, I have one, Robert. In that point, when you explain the age principle, the homotopy is, in the precise example you put, it's both an homotopy on the path and on the sections of the tangent, or only, okay, so you deform everything you can deform. Okay.
This is why you usually say that the homotopy is along formal solutions. So because you have a, this is what, wait. Yeah, this is what I draw here. So you have a family of maps, alpha t, which go from E to R2, and HT, which goes from E to the tangent space gamma t of, well, here I have a problem with parameters. But... So the family is of pairs. Pairs, maps to R2 and injections to the tangent space.
Okay. So it's quite general. Maybe it's only because of this example in the picture, but from almost any solution you can deform, almost from any initial solution you can deform it. I mean, the X principle is quite satisfied, like always, almost always, or not. No. It's not that general.
No, it's not true in general. Like, you mean because of this example or what?
Yes. It seems to be that.
This example it's one of those examples in which the H principle is telling you nothing because it's trivially satisfied, let's say.
Okay.
But there are other non-trivial applications. For example, I mean, besides the geometrical ones, I mean, proving H principles for geometric structures is highly non-trivial in general. But for example, you can also ask something like this. Let's say my differential relation is f prime very small, and where f is a map from R2 to R. Wait. Yes. From R2 to R3. So for example, you could start with a map which looks like this, which is a plane which is diagonally inclined, no? So what the partial differential relation is telling me is that it wants the derivative to very, very small, no? But this is not true here. So of course you can deform the plane into one which is just flat, and this will be a solution. But you can also ask something, sometimes it's very interesting to ask whether you have what it's called a C0 dense H principle. So what this means is that I can deform with a C0 small deformation. And so, for instance, this is true with some conditions. So, for example, yeah, let's look at an even easier example. So let's say the map is from R to R. And I take f equal x. So this wants the derivative to be small, but I cannot because the solution the derivative is big. But I would like it to be like this, right? So this is not globally true, but in a neighborhood of a point, I can do a C0 small deformation so that I have a solution. So what I can do is, if this was my original function, I can take a function which is like this. Now here, this is a solution because it's flat.
Okay.
So this is a non-trivial, let's say in dimension 1, this is non-trivial. In higher dimensions, this is a very, very powerful idea. The idea of saying near a submanifold of codimension, of positive codimension, I can find a solution with a C0 small perturbation and so on.
Okay, so in this example, you would say that this initial f does not satisfy H principle.
If you ask for a C0 dense, no.
Okay.
If it's not a C0, then you can just deform it back to here. And then you have a...
Okay.
But for some geometrical reasons, it might be useful to ask for C0 small and so on. So here the observation, it's trivial. Well, it's not trivial, but you need to think about it. And then the thing is that this simple idea has a very nice application when you sophisticate the idea, so to say.
How is this usually called, Robert? Is this wrinkling or?
This is called wiggling, I think.
Wiggling, yeah, wiggling.
Yeah, because in this, so for maps from R to R, the drawing is very easy, but in the other drawing that I was doing, it's more interesting, because if you take f from R2 to R3, sorry, yeah. So you look at this plane, and the relation is f prime small. So what here the idea tells you is not only that you can do it near a point, which is obvious because you also flatten a little bit at the point, but you can also do it along a line. So you pick a line like this. This is of codimension 1. And the partial differential relation is asking that the derivative is 0, which is very non-true, so to say. But with a C0 small deformation of the line, you can do it. And so this idea is to pick a line which goes like this. And this is why it's called wiggling. So if you pick a line which is like this, and this is C0 close to L, it's not C1 close because the derivative is getting very high, well, very, yeah. But basically this line that I'm drawing, it's almost flat all the time. So the tangent space is like this. So the tangent space is almost 0, 0, if you want. Okay.
Okay, thank you, Roy. Is there any other question?
I have maybe one question, but I don't know if it makes any sense, Robert. Like, can you like in your theorem where you embed like any non-vanishing dynamics in Hamiltonian dynamics, can you make this Hamiltonian dynamics to be one of those Ginzburg? Well, under the condition that your initial doesn't have any periodic orbits, can you embed it like in one of Ginzburg's examples?
No, because the problem is that, let's say, if you really think about it, in what you're fixing, well, let's say in the argument of algebraic topology in which you make homotopies, you lose completely the control of the dynamics. Because when you do these homotopies and so on, so when you apply, for instance, McDuffie's principle, you end up with a closed two-form globally, but the kernel, you don't know a shit about it because you obtain it by wiggling and so on. So the dynamics are completely crazy in principle.
Okay. Yeah.
And then something I can tell, well, I went long over time, but I think it's nice because it's.
Are you using questions to continue? Like, are you using questions as an excuse to continue your talk?
Exactly. No, but I think this is nice because it's an open question that I don't know. I think it's cool. It's not totally related to, but let's say. So there is a conjecture. This is called the periodic orbit conjecture. And with this, I will finish. So what this periodic orbit conjecture says is let X be a vector field in N, some closed manifold, such that every orbit is closed. So everything is a periodic orbit. Is closed. So the conjecture would say, then this implies that the length of the orbits is globally bounded. So of course the length depends on fixing a metric, but the fact that they are bounded does not depend on choosing a metric. Length of the orbits is bounded. Okay, so this is do you understand the statement? You have let's say a manifold filled with circles, which are orbits of a vector field. So you may ask whether the length of the orbit or the period of the vector field is bounded or not. So surprisingly, the answer is no. So that it depends on the dimension, but so in dimension 3 we are safe and this is okay.
I mean, bounded from above, or
from above, yes, because it's a positive thing.
Yeah. Okay.
Sorry, in this conjecture, do we have any conditions on N? Is it compact?
Yes, compact. If it's not compact, it's very easy to construct an example. So in dimension 3, this is true. I don't know who proved this. Epstein, I think. And then in dimension 5, Sullivan constructed a counterexample. And then in dimension 4, there are, no. Wait. Yeah, I think in dimension 4 there is also a counterexample. But the first one was by Sullivan. So you can have that the length of the orbit is arbitrarily large, even though it's always bounded for a fixed orbit. And okay. So then you can ask whether this periodic orbit conjecture is true if you add some conditions to the vector field. Okay, like what happens if the vector field is rep? What happens if, and so on, no? So who proved this? Fuck, now I don't remember his name. Well, it was proved that if X is geodesical, X is geodesical if and only if the length is bounded. Okay, so what this is telling is that any counterexample is not geodesical, for example. Okay, this implies that any counterexample is not geodesical. So a theorem that I proved this was, well, it's already in the archive. Well, in the archive, it's published. It says that, oh, well, and by the way, these counterexamples can be made volume preserving. So the volume preservation is not a problem. So if, so, well, let me put it like this. There is no Eulerizable counterexample. So being Eulerizable means being a steady solution to the Euler equations for some metric. And this is less. So being Eulerizable is less than being geodesical in principle. So there's something that I prove is that there is no steady Euler solution, which is a counterexample to the periodic orbit conjecture. But something that is open is whether there is a Hamiltonian counterexample. So this is open. I don't know. So is there a counterexample which is in the kernel of a Hamiltonian structure? Okay. And why is this related to this talk? Well, because of my theorem with Fran, you can embed a counterexample as an invariant submanifold of a Hamiltonian structure. But this is not answering the question, because the question says that the compact manifold is everywhere filled by periodic orbits. And then if there's the question is whether there is a Hamiltonian counterexample. So what with our theorem, what we can prove is that along a submanifold you might have a counterexample, but not globally. So this question is still open, and I don't know. I don't know if it's true or not. In any case, if there is a counterexample, it's not going to be geodesical, of course. Okay, so now I'm finished.
Okay, so we lost Cedric, I think, but let's thank Robert again. And see you in 2 weeks, but also next week we have a special session. So in fact, see you next week with Angel on Monday. Monday at 4, we will have a session about Chern-Simons by Angel from Itheman. Thank you